we can start his presentation on a uh, deep learning based for solar PV forecast.
Okay.
Okay, so I assume we do not need breakout rooms, right?
Yeah, because we only have 25 people. We were expecting a lot more. So I think this is the best. Yes, we can see your screen.
Okay, good afternoon to the audience. Thank you for joining my room. I will talk about deep learning based method for solar power forecasting with missing data. So this is the overall framework of the presented research work. This work was published in the expert conception on sustainable energy in September of last year. We know that the accurate PV forecasting is crucial to the power system planning, operation, and control. And in most existing works, we assume that the dataset is intact, which will be input to the machine learning models to make the prediction. However, in practice, due to various technical issues or power supply issues, missing data may occur sometimes. So this paper aims to develop a solar power forecasting model while there is missing data. The overall framework is illustrated in this figure, including an offline training stage and an online prediction stage. It is assumed that at offline training stage we have the complete data set, and then use this training data set, we train two machine learning models. One is the SRP, called the Super Resolution Perception CNN, the SRP CNN model, which is used for data imputation. And we also train another model named the Stochastic Configuration Network. This is a randomized neural network to do as the regression model for solar power forecasting. And then at the online prediction stage, we first judge if the online data contains any missing values. If yes, it will be imported to the SRP-CNN model to recover the full input data, which will then be imported to the SCN model, which is used as the regression model. So finally, the SCN model will output the predicted solar power. So to summarize, the SRP-CNN model is used for missing data imputation. The input length is 60 times 1 minus alpha, where alpha is the missing data ratio. If we assume a missing data of 50%, then the input of the SRP-CNN will be 30. The output will be 60. And for the solar power forecasting model, for the HCM model, the input data is the previous solar power at the previous 60 data steps. So the input length is 60, and the output length is just 1, which is the solar power of 10 minutes later. The data set that I used for validation is from the University of Queensland. It can be accessed from this website. The data resolution is 1 minute. I took 2 years of data from December 2015 to November of 2017. For each year, we have 4 seasons, the summer, fall, winter, and spring. And for each season, the data in the former year is used as the training data, and the data of the latter year is used for testing. Then I will give a brief introduction to the 2 machine learning models. The first one is the SRP-CNN. The full name is Super Resolution Perception Approach, Convolutional Neural Networks. This SRP-CNN was initially proposed to reconstruct high-frequency data from low-frequency data of industrial sensors. So the input of the SRP is the low frequency data. We can also say this is a short vector, while the output of the SRP is the high frequency data, which is the long vector. So taking this nature of the SRP CNN, we propose to use this method to recover the flawed data set so that we can make solar power forecasting. This SRP CNN is actually a deep CNN with 3 parts. The first one is feature extraction consisting of one or more convolutional layers, and then follows the information supplement part. This part consists of several residual blocks, 1 to n. In our case, we used 16 layers. This reconstruction part reconstructs the feature vectors of each instance into f sub-vectors, and each of which has a length of df. These vectors are then rearranged as the estimated flow data. The mean squared error, the MSE, is used to train the SRP CNN, and the network parameters are optimized using these formulas. This is the residual error between the estimated flow data as well as the true flow data. For the HCN, we use it to forecast the solar power using the previous 60 points. This is a randomized neural network, meaning that the input weights and the bias at the hidden nodes are all randomly assigned. Then the output weights are computed using matrix operation analytically. So different from existing algorithms like the extreme learning machine and the RVFL, the hidden nodes are incrementally added and constrained by an inequality that will ensure the approximation ability of this neural network. The major advantage of this network is that, as I mentioned, the input weights were randomly assigned. So compared to traditional neural networks, which tend to be trained by backpropagation using gradient descent, this training of this network is free from gradient descent. So this computational burden of this neural network is exceptionally low compared to traditional neural networks. Additionally, we say that the output weights are computed analytically. It's also free from gradient descent. So some issues of gradient descent, like local minimums issues, will be avoided by this neural network. So to summarize, the two advantages of the neural network is, one is the training speed. The second one is the good approximation ability due to free from gradient descent training process. This slide shows the results with the proposed method. We use the normalized root mean squared error as the metric to evaluate the performance of the proposed method. This figure on the left shows the true and estimated data under different missing data rates. The right table summarizes the forecasting results. We also compare the backpropagation-based neural network and LSTM with the proposed SCN. And then under different missing data rates, the results are all shown, and the average values of each season are also given. We can see that even when 95% of the input data is missing, the average error only increased by less than 0.75% from 10.21 to 10.96. So this indicates the excellent missing data tolerance of the proposed method. Then we compare the proposed method with other two models that can tackle missing data. One is the random forest with the surrogate splitting. The second one is we use the linear interpolation for missing data imputation, and also use the SCN as the regression model. We can see that with all the 4 seasons, the proposed method maintain a relatively low error, while the other two methods, the errors of them increase significantly as the increasing ratio increases. So these are the references to the models. Thank you. That is all for the presentation. Thank you.
Thank you. Thank you. Anyone has any questions? Anyone, you can unmute yourselves and ask any questions you have. I think maybe you all have already listened to his presentation and interacted, because I think room 1 and room 2 had a lot more presenters. So if you have any other questions, you can directly message him. Or so let us start with the last rooms, because I think the last rooms didn't have many people and the first 2 rooms had a lot. So I think we'll start with Aditya from the last. Aditya will speak about exploring the chemistry of thin film deposition using ALD. So is that okay, Aditya? Can you go next?
I can go next. Because there's also not many people in my breakout room.
Okay. Jiawei, I think you can go. Jiawei will be speaking on blockchain application for P2P energy trading. Yeah, you can share your screen whenever you're ready.
So, hello everyone. Thanks for attending and listen to my research. And my research title is Blockchain Application for Peer-to-Peer Energy or Power Trading. So this is the general structure of our project. At the top is the blockchain technology. If you have do some pre-study about blockchain, you will know that it includes the smart contracts, the timestamps, and the transaction information, as well as its own cryptographic method, such as hash function. So the main function of the blockchain technology is to store and record the transaction information. First, the specific information of transaction will be translated by the hash function to a set of code, so that this transaction could be protected. At the bottom is the microgrid, in which peer-to-peer energy trading is happened. And the blockchain provided the platform for the prosumers to trade their energy directly with each other, including the information exchange, the contract negotiation, and something like that. This page expresses the method of how to set up the blockchain technology. First, it is started from the Infura, which is a company that gives us the opportunities to start our own blockchain project. It will first initialize or give us some tokens so that we can set up our own blockchain. And then we use Geth, Go Ethereum, which means our blockchain project is set up based on Ethereum platform. And then we use Web3 package to connect our smart contract with our blockchain, and use truffle package from Node.js to deploy our smart contract on our blockchain technology. At the bottom is the OpenRT, which is a real-time simulation machine to simulate the peer-to-peer energy trading. we set up our own UDP, User Data Protocol, to transfer the data from the peer-to-peer energy trading to our own database. And then we pump this data from our own database to the Web3, which means to our own blockchain technology. So this is how the blockchain combine with the peer-to-peer energy trading. This is the ERC20 cryptocurrency, which means we set up or initialize our own cryptocurrency, which name is Alicoin, to be traded with energy in our project. This is the interface of the prosumers, the microgrid, which shows the energy demands or surplus energy that could be traded with each other. And this is the interface that we created for each users. If they have their own energy demand, they can click proceed to settle bills with smart contract. And then its energy proposal will be announced within the microgrid. If someone has their own surplus energy, they can, so that their energy demands will be fulfilled. This is the general structure of each block of the blockchain. As you can see, it's transaction hash, which is be translated from the specific information of transaction. The specific information of transaction can be seen as below, where you can see the address of the smart contract and the sellers. The address of the sellers is OXA21 blah, 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 and through the smart contract. And he spent actually 0.016 blah, blah, blah Alicoin to trade it for his energy. This is the interface of the smart contract. As you can see, we deploy our ERC20 tokens from this smart contract. And at the below is the according transaction that happened depending on this smart contract. This is the format of our own database, that this data are pumped from the database to our own blockchain. As you can see, how much energy is generated, how much energy is used by this prosumer, and how much energy, how much is the surplus energy that could be traded within the microgrid. This is another database that record the usage for each prosumers within the microgrid. As you can see, there are 5 different prosumers in our microgrid. One is OXA21 blah blah, one is OX05 blah blah blah. So these are all address of our prosumers within the microgrid. So in conclusion, we deploy our own proof of stake consensus protocol based public blockchain, which could ensure the security and the transparency of the transaction for the distributed system, which means the microgrid. And from the peer-to-peer energy trading, the data is generated and be pumped to our own blockchain. So this is how our project works. So that's all for my project. Thank you.
Thank you. Thank you. That was actually quite interesting. So anyone has any questions for Jiawei regarding blockchain or peer-to-peer trading?
Yes, Jiawei, I have a question. Have you compared like the energy trading of your Alicoin with other existing coins?
Actually, we set up the cryptocurrency is to make the transaction goes fast, because cryptocurrency trading could happen very fast on the blockchain technology. We can also use other cryptocurrency such as Ethers. And this is the only choice besides our own cryptocurrency, because our blockchain is set up based on the Ethereum. So I think there's no difference between use our own cryptocurrency or use Ethers.
Okay, thanks.
Yang, one question from my side would be, there is one attempts like this called as energy web token. So how is it different from that?
Actually, the token, for example, as I just showed on the previous page, is that our token is based on ERC20 tokens. So I don't know where the token you have mentioned depends on which kind of stance. Like, for example, there are ERC20, there are ERC77, but in my opinion, they have no big difference. The main difference between between different cryptocurrency is their blockchain types. So in our project, we use proof of stake public blockchain. And for Bitcoin, for example, Bitcoin, they use proof of work public blockchain. And now for Ethereum 2.0, they actually use proof of authority blockchain. So it is the types of blockchain that can define the function or the difference between different cryptocurrency.
Can you drop your LinkedIn link in the chat so that I can maybe connect to you through LinkedIn?
You mean my email address or contact number?
Yeah, that would also do.
Sure. So your name is, oh, I see. Where I can.
Just put it on the public chat. I'll pick it up from there.
Okay.
Does anyone have any more questions? Don't be shy. You can network. There are only 28 people, so please ask questions if you have any. One question I'll have is actually blockchain required? Like, do you think this security is required for energy transaction, or can we do energy transaction without blockchain also?
Yes, of course, because the peer-to-peer energy, when peer-to-peer energy trading comes out, actually researchers has no connection to be made with the blockchain. But we found that actually peer-to-peer energy trading is a kind of distributed system that requires decentralization or to eliminate any central authority. So we think this feature could match blockchain technology well. And blockchain technology is just to improve the security and make sure the transparency of each transaction. It does not improve the efficiency or to improve the quality of transaction itself. The blockchain cannot do that. It's just to do some security work or make these transactions more transparency, and all the prosumers within the microgrid could see the details, but the prosumers outside the microgrid could not get the internal information of each prosumer. So this is the advantage of blockchain.
Okay, understood. We'll also be taking a group photo, I think, in the end. So please be connected. Like, does anyone wants to go next? Like any researcher? Anyone wants to go next?
Maybe I will go next.
Okay, thanks, Mohasa. Yeah. Share your screen.
Yeah. Is my screen clear?
Yes.
Okay. So I'm also working with GRV in the same project. So my work is mostly towards technical side of the power system. So the topic that I am presenting is grid feasible peer-to-peer energy trading. So my name is Dr. LP Sampath. I'm a research fellow in NTU. So this is the project website where I'm working. So in this presentation, like mostly I will talk about this peer-to-peer energy trading and what are the new requirements and concepts evolved with it. And first I will start with the recent reforms in the distribution system and why we need peer-to-peer energy trading. And at the end, I will present some case study with some conclusions. So mainly because of these greenhouse gas emissions, there has been certain changes in the climate and the adverse effects over the globe can be seen. So because of that one, the decarbonization of energy sector has been under the discussion for over a decade and increased like as a result, they have suggested to like phase out many of the coal power, natural gas, and related fossil fuel based power plants. And as a result, penetration of renewable energy sources such as solar PV, wind power has been increased mainly in the distribution system. In parallel, the advancements in energy storage systems and communications technologies, both in efficiency and cost reduction, was also there. And because of these many changes, the traditional elements, or as we call as consumers in the distribution system, are no longer a passive devices or as a passive entity. They will be more active with solar PV, energy storage systems, and with dispatchable loads. So we a new term has been introduced called prosumer, means an entity can produce or consume at a particular time interval depending on its preference. So like when many prosumers are there, these prosumers, since they can either produce or consume, rather than like talking with the utility, or else rather than just making contracts with the utility, they can exchange power among themselves also. To facilitate such power sharing, peer-to-peer energy market concepts has been evolved. And there are many frameworks suggested over past few years. And in this work also, I will introduce what this peer-to-peer energy trading is conceptually. So different to the centralized energy management, which has been done by the distribution system operator, in peer-to-peer energy trading, we will provide an information layer, a common layer, so that all the sellers and buyers can provide their bids. This can be distributed as well, means like one buyer and seller can talk separately and negotiate for price and power. Likewise, they can create bilateral energy trading contracts. Like in this figure, it's like let's say at a particular market interval, means it can be 15 minutes, it can be 1 hour. Sorry. So there will be set of producers and set of consumers, and some prosumers can omit from trading at a particular interval as well. Each prosumer will be seeking from to which consumer it will sell power, because it will always seek to maximize its social welfare. Maximizing social welfare is also we can interpret as minimizing the generation cost. And as such, they will try to form trading pairs as much as possible. So each and every since each and everyone is like trying to maximize its own outcome, game theory has been much popular in this area. And apart from that, continuous double auction, ADMM, dual decomposition, and many such market clearing algorithms has also been proposed. So if we see the physical locations of these prosumers, let's say if they are only in a particular node, let's say like this, so then sellers and buyers can trade as they prefer without incurring any power losses or voltage or congestion issues in the distribution grid. But however, sometimes these prosumers may be located at different locations in the distribution grid. So when you negotiate, maybe and the other thing is these prosumers are not willing to share their information. Location also can be another aspect, because someone else can collect that information and predict their outcome, then they will lose in market concepts. Let's say some power sharing happens between seller at node I and buyer at node J. Then for this power transaction, it will incur some power losses, and also depending on the other power transactions in the system, it can also create voltage issues or congestion issues. Then the DSO has to do some additional tasks to support ancillary services for these P2P transactions. That means there should have a mechanism so that DSO can recover whichever the cost of provisioning ancillary services to facilitate these P2P transactions. So this work and the case studies, everything, will talk about how we can recover those costs from the respective trading pairs. So one of the basic tools used by the DSO to compute these ancillary services requirements, or else for market clearing, is optimal power flow. That is a traditional one. So since it is an optimization problem, it has an objective function which is basically minimizing the cost of dispatch. The constraints are the power balance at each node, bus voltage limits. The power balance includes all the power flow equations also. Then branch flow transfer capacities, means like when you're taking power from one node to the other node, which source you need to dispatch. That will be decided by the DSO in a centralized manner. But right now, all the transactions are happening and the contracts are formed decentralized in a decentralized manner, and the DSO may not know all the information, and the prosumers are not willing to share with the DSO also. One of the important features of this OPF is that in mathematical form, there will be dual variables, since it is an optimization problem. These dual variables will have a physical meaning. That is, the dual variables at power balance constraints will reflect marginal cost of power demand at each bus in the system, depending on the power flow at which the OPF was executed. So then mathematically we can represent the per unit ancillary cost of transferring power from node I to node J would be the difference between the LMPs of the respective nodes. So now this particular quantity should be included in the market mechanism of P2P energy markets, so that prosumers will consider this as a factor to trade off between, or when they match trading partners in the market mechanism. The algorithm proposed in this work is alternative direction method of multipliers, and it has a two-stage mechanism. Means like here in this context, prosumers will first negotiate with each other, like here, and they will exchange. First, they will execute a local optimization. Means like they will see what are their resources and how much they can dispatch considering their own local constraints. And depending on their preferences, they will communicate with other prosumers, and some price update is involved. Means like at which price will he or she will sell or buy power from. And then this part is the where it will communicate with the DSO, since it needs to know some get some idea on how much ancillary costs will be associated with this particular transaction. Means if ancillary costs are higher, then he can select another prosumer instead of the one he has already selected. So this is how the two parties like DSO and prosumers will be exchanging information. So the DSO at every market iteration, it will collect all the power injections from all the nodes and execute an OPF and compute DLMPs. As we know, this, like when injections are changing, the OPF structure will change and the DLMP update will change. However, provided that all these local optimization problems are convex, alternative ADMM will always gives you a convergence after some finite number of iterations. So in the case study, we have considered a standard IEEE 33 bus network and applied this ADMM based coordination optimization algorithm. In the case study, we have considered 6 producers and 7 consumers. It will work with any other number also. This is just roughly assumed and taken. To support with ancillary services, we have considered 5 additional sources, like it can be diesel generators or as other connections to the main grid apart from the main point of common coupling. This algorithm is fully coded in MATLAB, and the optimization problems has been run with solved with Gurobi. So here, talking about the results. Here, I'm not talking presenting any equation, since it will be in papers, and if someone is interested, I can send the paper, and that will be online. So just the idea I will talk, and so if someone has any questions about these results, we can discuss later. So here this figure shows how it iterates, and here I have the black color shows the DSO OPF iterations, and the residual has been shown. Residual means, like, let's say from one iteration to the other iteration, the nodal injections will be changed. So what is the difference between the two? So it is coming down. So after some tolerance, we will terminate from the algorithm. So here there will be 13 curves, blue and red curves. So to show that every local algorithm, how it will terminate to how it will comes to conclusion. Because like here, there will be 13 prosumers and 1 DSO. That means 14 market participants. They all will run their own algorithm, and everything should terminate at the end. So for this example, it has been taken 958 iterations, and the time taken per each iteration also has been shown here. So here for OPF execution, it's a bit expensive compared to other local optimizations. And like case studies has been shown in under two scenarios as well. One is like, let's say if you do not consider ancillary service, means like if prosumers are like allowed to exchange power on their own, then how power transactions will happen in the grid. So here you will see that consumer one, he won't be able to share power in when ancillary services are considered, or else he is not interested because cost would be very high for it. But the other way, it will be able to transfer without any problem. And the other thing is that can create some infeasibilities in the grid management. Then this I can call as grid utilization fees. That is the LMP difference. Let's say from C1 to P1, $1.254 per hour. That would be the value. Here some negative values are there. Negative values means when some power transactions happen from P3 to C1, let's say, that will gives a reward. Means like it will reduce the losses or congestion or voltage issues in the distribution system. So it will always not reflect as a cost. It will be a reward also, depending on the location and other power flows in the system. So here the market clearing, how each consumer selects the other, each consumer producer selects others. So for this example, I have plotted the consumer 6 data. So here black curve shows its marginal welfare. So whichever it is whichever the other producers having marginal cost less than its marginal welfare, he will be willing to buy from. So if something is higher than it, let's say for instance producer 2, so its marginal cost is lesser than the marginal welfare of the consumer. However, with the ancillary cost, it has been increased, so he's not sharing any power. Power sharing or like how much the amount of power that consumer 6 is taking from each producer is shown with green bar. So here you can see from producer 2 and like it's not taking any power because of the ancillary services cost. So he will select like others, and it will import more from other producers instead. So going into conclusion, so in this ADMM based coordination algorithm, it enables like P2P market clearing under the consideration of ancillary services. Also, we will still respect the privacy concerns, because ancillary services are always computed centrally. So you need to take some information, but here we have only shared the power exchanges, which is not that private. So you can, the prosumers will be anyways sharing that power exchanges with other prosumers in the system. The case studies are depending on are based on 33 bus system. Like as I shown, the computational time is also sufficient and or acceptable with the our standards. And one of the important thing is that trade-off. Like normally the consumers are and producers, when they come up to a market clearing point or market equilibrium, they will just consider the costs and welfare. Right now, there will be a third quantity.
So here is the data for rooftop specifically. So on your upper right side, you see the share of rooftop in total installed capacity for India, and it is minimal, is what we believe. But on your lower left side, you see different segments of consumers. So practically 75% of all the rooftop PV installations in India, they are coming from commercial and industrial customer. The reason we believe is because of the high electricity tariff rate, because they are cross-subsidizing the residential and agriculture field. So this is the segmentation. We want all the segments to grow. And you see the absolute number, they are reaching towards 6 gigawatt, whereas the target is 40 gigawatt. So we still have scope to grow. So what are the achievements and challenges coming to my research topic? So these are the achievements. We have reduced the solar PV cost considerably, like 86% of drop in 8 years as per the IRENA report. When I say this drop, this is for the auction price that SECI has been conducting. Second thing is the share of solar PV is overall energy. The share of solar PV in overall energy mix has increased. And the third is we have developed our own installation capacity. There is an industry which install the solar PV plants, and they are also looking for looking to expand in the foreign countries. What are the challenges? We have limited rooftop capacity addition. We still have 5 gigawatt. I told you the target was 40 for rooftop. Second is the manufacturing industry. We have to work on that. And third one is the sustainability. We have subsidies and government support for this industry, but if it has to self-sustain, it has to grow on its own. And this is where the role of policy rather than the passive role would come into picture. So what is this research all about? So I'm trying to find what is the effect of federal and state specific PV policies on the deployment of rooftop PV, and how policies influence stakeholders, and also there is a vice versa, how stakeholders influence policies. This is what I'm studying. So for that, we have to see what are the different instruments that we can use. So these are the specifically monetary instruments, different kind of instruments, grants, tax incentives, subsidy, regulatory instruments, and debt support. You see, some things are very tricky. In tax incentives, the last point is accelerated depreciation. It is more like a accounting mechanism, but for the convenience, I have considered a tax incentive. I'm still exploring and reviewing the literature so that this can be made in a great way rather than this. So this is, I'm still exploring. What is the way forward? How do I go for this? How do I go with the research statement? So these are different ways that I have figured out and I'm still exploring. First one is we do cost benefit analysis. In a sense, we find the value of solar PV in a distribution grid. Second thing is load curve analysis. We know that there is a demand curve and there is a solar PV generation curve, and then we can find out the optimum value of solar that can be put in the system without any storage part. That
Okay, so these days microgrids are getting quite popular due to its distributed nature. The definition of microgrid according to US Department of Energy is given as it is a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries. So a microgrid can work in grid connected mode as well as islanded mode, and therefore they give some of the major benefits, such as it reduces the peak load demand, peak grid demand, and it also reduces the line losses, because most of the distributed energy sources are located on the load end. So it is a small amount of energy is also only required from the grid side. So most of the power is being fed from the grid itself. Most of the power is being fed from the prosumer itself. Hey Sarvesh, are you able to see which screen you are able to see?
Microgrid and their benefit.
Okay.
Maybe you can just
able to change?
Yeah, microgrid configuration. Yeah, now.
Okay, now it's okay. So the major benefits of microgrid are microgrid. Due to microgrid, so many renewables are getting integrated with the grid system, with the complete system. So the burden on conventional grid is reduced. And second thing is that as the burden is reduced, so transmission losses from the grid to the load end is also reduced. Therefore, the cost of energy to the local loads is also reduced. Moreover, when there is more generation of energy than the consumption of for the locality, it can be fed back to the grid, and therefore this can aid as a economic growth for the locality. One more thing is that so in the case of grid failure, suppose this microgrid is able to feed the local loads and the critical loads. So this also incorporates resiliency. The distributed energy sources are mostly renewable in nature. So in this sense, we can see that this also counters the climate change by reducing the carbon footprint. So here, a typical structure of a microgrid network is shown over here. And the presented microgrid comprises of single phase AC grid, local load, wind energy generation system, solar photovoltaic generation system, and battery energy storage system. So here we see that a number of power electronic converters are required for the proper operation of the microgrid. In this system, we have three power electronic converters. One is grid side converter, which enables the input and output power flow from the microgrid system. Second is the bidirectional converter, which enables the bidirectional power flow between the battery energy storage and the DC link. And third is the generator side voltage source converter, which enables the optimum power generation from the wind energy generation system. So next we will discuss the control of the different control converters. So here is the control structure for the generator side converter. We know that for extracting optimum power from the wind generator, we need to run the generator at a particular speed according to the wind speed. So for this, we have used wind hill climbing algorithm for the generation of reference generator speed, so that we could extract optimum power from the wind generator. This reference generator speed is compared with the generator speed, and the error is fed to the PI controller. The output of the PI controller is taken as the reference quadrature axis current. Since a permanent magnet synchronous generator is utilized over here, the reference direct axis current is reduced to 0. Now the inverse Parks transform is utilized for the DQ to 0 to ABC transformation, and these reference currents are compared with the sense stator currents and fed to the hysteresis controller for the generation of switching signals for the generator side converter. Second is the control of bidirectional converter. The bidirectional converter controls the battery current in the microgrid. Here in this control system, in this system, the DC link, this system can work in islanded mode as well as grid connected mode. So there are two modes of operation. So when it is in grid connected mode, the DC link voltage is controlled according to from the grid side converter. However, when grid is not available, so grid side converter will not be able to control the DC link voltage. In that case, the bidirectional converter will control the DC link voltage. So when the reference DC link voltage is taken from taken according to the voltage at which the PV array extracts optimum power can be extracted from the PV array. So again, the reference PV voltage is taken from the hill climbing algorithm, and then this is compared with the PV array voltage, sensed PV array's voltage, and fed to the DC link voltage controller. So when grid is available, it goes to, it is taken as the W loss component and weight of the loss component, and when grid is not available, this component is taken as the battery reference current. So when grid is not available, the excess power will fed to the battery, and if there is less power, then the power will be the battery will support the local loads. So this reference battery current is compared with the sensed battery current and fed to the hysteresis controller. The hysteresis controller generates the switching pulses for the upper and lower switches of the bidirectional converter. Third is the control of the grid side converter. So as when grid is available, then only this converter will operate, and when the DC link voltage output DC link voltage controller's output is the loss component in this equation. Moreover, for accelerating the performance of this system, we introduce feed forward terms. So since there are three components, wind feed forward, PV feed forward, and battery feed forward terms are utilized in this work. So wind feed forward term is taken as the power of the wind generation divided by the terminal voltage. Terminal voltage is the RMS voltage of the grid. Similarly, we have calculated the PV feed forward term and the BES battery feed forward term. So for then we generate the reference grid current, which is the product of the unit template and the net component. The net component is the net sum of the all the feed forward components, and the unit template is the ratio of the filtered grid voltage and the peak grid voltage. We take the filtered grid voltage because it is possible that in weak grid condition, the voltage would not be sinusoidal. So in that case, if we take the actual grid voltage, then the unit template will also be distorted. And in this scenario, the reference grid current will be distorted, and finally the actual grid current will get distorted. So once the reference grid current is generated, it is compared with the actual sensed grid current and fed to the controller for the generation of switching signals for the grid side converter. So next is the structure of the FA-DSOGI. This is the structure utilized for the extracting the filtered voltage and current. So as we know that we have utilized a non-linear, so most of the loads in our home are non-linear in nature. So we have taken the filtered load current as well as filtered voltage for generation of the weight component. So this structure is a frequency adaptive damped second order generalized integrator. So we can see here that even if the load current is just in the upper figure, that even if the load current is distorted, the output of the filtered current is sinusoidal nature. Moreover, since this filter is frequency adaptive, so it can adjust the minor variation in frequency. Here, although I have just for the sake of showing, I have taken the frequency change from 50 to 55 hertz. So even such a major change, it is able to adapt. So next is the performance of the presented system. The performance of present system. This slide shows the steady state performance of the presented system, where we can see in A that all the stator currents, three-phase stator currents of the wind generator, all are sinusoidal in nature. Moreover, the rotor position is effectively estimated, and it is varying between 0 to 2 pi. Second is the MPPT performance and of the solar PV array, and here also we see that an excellent MPPT performance is observed, and 99.8% of MPPT is observed. In the third, we see the generator current. First is in C, we see the third first is the generator current, and second is the PV current. PV current is settled at the MPPT current, IMP, and in this C, the third is the load current, which we see that it is not sinusoidal, it is distorted, and even if it is distorted, the grid current is sinusoidal in nature. The fourth one is the grid current. The last in D is when the grid is charging the battery. In this condition, we can see that the battery current is negative, so it is being charged, and the voltage and grid current are in phase. So it is supplying to the grid is supplying to the battery, and no other renewable energy generation or load is connected at this moment. This slide shows the dynamic performance when the wind is energy generation system wind speed has been reduced from 12 meter per second to 7.2 meter per second, and we see that this has resulted in reduction in the power generation from the wind energy generation system, and similarly the wind feed forward term has also reduced. This has resulted in the reduction of the net component, and therefore the grid current will reduce in this condition. Similarly, in C2D, we see that the performance when the solar insolation is changed from 1000 watt per meter square to 500 watt per meter square. So accordingly, the power generation from the solar PV array also reduced, and it has settled down to almost half at what it was around half. What it was at 1000 watt per meter square, it has come down to 50% around. This has also impacted in the similar way. In all this result, only one parameter is changed and others are not altered. In the first two cases, only wind speed was changed, and the later two results, only the PV parameter was changed. So in both the cases, the net component has reduced, and therefore the injection of the current into the grid also reduces. So power being fed to the grid will reduce. These are the power quality performance. In the first case, the power quality performance when wind and solar are feeding the grid and load. So wind and solar are operating at their rated condition. Wind is operating. Speed is set as 12 meter per second, and solar insolation is set as 1000 watt per meter square. So we can see here, and the load is around 1 kilowatt in this case. So we can see here around 3.15 kilowatt of power is being injected into the grid, and minus sign index shows that the power is being injected, not being drawn from the grid. Here we can see that the THD of the grid current is around 3.2%, which is well within the prescribed limit under various IEEE standards. The last one result is showing the power quality performance when grid is feeding the load. Here we can see that the load current is non-sinusoidal, and it has a THD of 13.3%. Here we can see that load is around 1 kilowatt, 0.94 kilowatt, and power being fed from the grid is around 1.03 kilowatt. Both voltage and grid currents are in phase with each other, and we see that even when the load is non-sinusoidal in nature, load current is non-sinusoidal in nature, the grid current is sinusoidal. So this is here, and the grid current THD is well within the limit with the use of presented control. So these are some of the conclusions which can be drawn from this work. A satisfactory operation of wind, solar, BES based AC microgrid under various operating scenarios has been exhibited, and the experimental results under steady state and dynamic condition are found to be satisfactory. The presented system follows the IEEE 1547 and IEEE 519 standards for grid connected system, and therefore present a feasible solution for AC microgrid with distributed energy resources. These are the system parameters used for hardware validation. These are some of the references. Thank you.
Thank you, Shadab. It was interesting. Does anyone have any questions for Shadab? Anyone? We're also running late on time, so I think we have time for one more presentation. Does anyone want to go ahead with it? Any volunteers?
Yeah, I will present.
Thank you, Brijesh. So I'll just make you the co-host. Yeah.
I hope my screen is visible to everyone.
Yes, it is.
Okay. So let's begin. This is my topic. This is the co-simulation framework for energy performance in buildings. So let's look at what is the co-simulation. So I have built it because I have seen the many students topic and I thought that it would be great that I will present later because everyone now able to relate this topic. So suppose we have to plan a city. So in that city, there can be a building clusters. To power this building cluster, there can be a renewable grids, there can be a thermal grids. For power trading, as our fellow researcher talked, there can be a connected systems. So how we can holistically model this system in an integrated manner. So for that, we need to develop some kind of interface where different kinds of model can exchange data among themselves so that they can be operated in an optimized manner. So this is about the co-simulation. Here we model different systems into different simulation tools, and then we integrate those simulation tools with the co-simulation interface where they can exchange data for the optimal operation. Similarly, if we talk about the building level, in the building also, there are many components that interact with each other. So for example, here this is the occupant. To satisfy its thermal need, it can operate the ceiling fan. It can also operate this HVAC system, and there can be integration of this HVAC system and this ceiling fan. So here also the same thing applies. Like here, we can also model the different components in different tools, and then we can provide a interface where they can exchange data among themselves for their optimal operation. So this is the idea behind this co-simulation. Now let's talk about its development, how we can develop a co-simulation. So here, this is a particular example, but let's take it as a broad way. So suppose we have to model city airflow, so we can model it in some CFD simulation tools. So, and suppose we have to model some renewable system with the building, so we can model it with this energy plus simulation tool. And also suppose we have to model this trading kind of system, then we can do it with the MATLAB or Python. And these are some intermediary tools that can provide the data communication between these tools among themselves. So this in this way, this co-simulation tool can be developed. So here, this is the example of co-simulation between CFD tool and the Energy Plus. This is the interface which is connecting this and this to software, and this framework shows like how data flows from one tool to other during the simulation. So let's see the example of these things. So here the example is this same house. Here this cooling effect is basically the elevation in temperature, set point temperature that ceiling fan facilitate to achieve a particular level of thermal comfort. So we can how we can model this with the co-simulation. So we can model this ceiling fan and this thermal energy storage system in the CFD tool, and the rest of the buildings with the HVAC system in this building energy simulation tool, and then we can integrate these two with the co-simulation interface. So now take a deeper example of this. This actually shows what kind of data goes and what kind of data requires for a particular simulation tool during the co-simulation. So here this example shows that this model needs the surface temperature data of this model, and this model shows that it needs the heat transfer coefficient from this model. So in this way, data transfer happens. And if we see the performance, we can see that if we see the RMSE, there is a 50% difference. So we can say that co-simulation facilitates the 50% improvement in prediction of the system performance. And this is the temperature performance with the experimental data, and we can observe here that this co-simulation is more replicating the experimental data compared to if we model in a one simulation tool. Now let's see another example of co-simulation. So this is the Team Sunya house we have built in IIT Bombay, and this is the experimental setup to control the air condition of this room. So in the market, there are these air conditioners are operated on constant set point temperature or PI or PID controller. So what we did, we have developed and implemented the model predictive controller. So model predictive controller basically anticipates the future disturbance and provides a trigger to this different system based on the constraints. So this is the example of real-time co-simulation. This is the controller that is developed to implement the model predictive control in this room. And this model is so that this room can be modeled, and this model can be integrated with the hardware so that the necessary data can be provided from this model to this hardware, and this hardware can send a trigger points to this actual system. And if we see the performance of this system, so here we can see that this model predictive controller saves 70.5 and 8.8% energy saving compared to this conventional control of this FBS, conventional control of the air conditioning system of this room. Okay, so now let's see the another example. This is the case study. Actually, here it compares the thermal comfort and the energy consumption in two different case scenarios. So here, the hypothesis is that this guy is writing a letter to this guy that my thermal comfort is better than you. So this guy is replying, no, I have a better thermal comfort and I am also saving some energy. So he's wondered like how can you do this? So what this guy did, he has implemented a smart AI driven controller in his room. So let's see how he has achieved the thermal comfort and also saved some energy. So here basically he implemented this AI driven controller where this AC set points and the ceiling fan speed is controlled based on the thermal need of that person. So if we see the performance of this controller, so this is actually tracking the thermal comfort of the previous one, that is the guy without ceiling fan. And see, during his track, this controller provides the different set points and different rotating speed to the ceiling fan and the HVAC system, and we can see that this controller facilitates the 28% saving compared to this traditional case. So in this way, this our second guy is able to save energy and also achieve the thermal comfort of this one. So now we go to this conclusion. So conclusion is we should see the system in a holistic manner, not as an individual level, because everything is connected. And way forward is that co-simulation is still a lab-based technique, like it is not standardized and not commercialized. So dissemination of knowledge should be there in the market for its commercial purpose. In this way, I am ending my slides. Thank you.
Thank you, Brijesh. Does anyone have any questions? Yeah, I think no questions, but
I have
yeah,
one
sorry.
question.
Yeah.
Yes.
Can you go to slide 7?
Yes.
Yeah, this case study, the left one doesn't have the ceiling fan and right one has ceiling fan. So you are basically comparing the effect of ceiling fan in presence of AC.
Yes.
Okay, so if we have AC, I mean, if we have ceiling fan combined with the AC, then the thermal comfort will be more and
yes, that's what this study says, that because the thermal comfort is not just a temperature, like we are just operating air conditioner in the room, but our thermal need depends on the 7 kind of variables that depend that includes the air velocity, the clothing that we wear, our outside environment, our indoor environment, our physical activity, metabolism, everything is contributing to our thermal comforts. And what we do, we generally just decrease or increase the set point of this air conditioner. So this is not the actually correct way of achieving the thermal comfort. We have to incorporate the air velocity also. Like, it is a general intuition that if we operate the ceiling fan, we feel better, right? So why don't we use in the practice in the commercial building? Like in residential building, we do this, but in the commercial building, it is not done as usual. So that's why, and also, like, there are now different AI driven controller are coming into the market that controls the different appliances in our room. So in this way, if we are achieving the thermal comfort and we are also saving energy, so what's wrong in that? So we should apply those kind of techniques for operation of commercial buildings.
So here, like, you have two components, like fan and AC, and in the left case it is only AC, but you
Yes.
are controlling the operation of both ceiling fan and the AC, so that this right guy has a more thermal comfort than the left guy, and also
Yes.
less energy consumption.
Yes.
How are you controlling energy consumption? I mean,
I am not controlling energy consumption. I am tracking this thermal comfort, right? Suppose here this red one is for the AC and fan, and the dotted one is the reference point. So if you see that it's tracked this reference point with the different set points and the ceiling fan speed.
that I
Okay.
got, but what about energy consumption? I mean,
So energy consumption is that is suppose you are suppose X amount of energy is consumed at the 20-degree set point temperature. Now you are operating fan and you can increase that set point to the 26. So now you can see that we have elevated the set point temperature to 26 compared to the earlier 22. And the power consumption of ceiling fan is very less. It's a 40 watt, right? So we are see how much we are, if we just apply the simple numeric MCP delta T, you can see how much energy we can save. And just you can add the full power of ceiling fan. Then also you can see that this kind of energy is saving.
so this system can be useful for the personal cooling as well as commercial cooling, right?
Yes, yes. Actually, we have applied in teams in my house. So, yeah, you can come to my lab and I will show you.
Okay, thanks.
Is there any other questions?
Any other questions? So yeah, maybe nothing more. Anyone else wants to present, or should we call it a day?
Are we having group photo or?
Yeah, but we can have a group photo if everyone willing to open up your cameras. Thank you. Just give it a moment so that everybody's opening the camera. Thank you. Yeah. And yeah, just a minute. Just take a picture. Yes, done. Thank you. And if you're free to leave your LinkedIn in the chat so that people can follow you, please, if you want to. I think everyone is into research here, and we have a very specific target audience. If you want to expand your network, please please leave your LinkedIn in the chat, and also you can join the Discord server if you want to. The Discord server is also in the chat.
Yeah, the Discord might be easier because I don't think we'll have access to the chat after the Zoom is done. So if you want to leave your LinkedIn, it might be better to do it in Discord.
Yeah, you can join my Discord. Thank you for coming. Yeah. Any questions?
If anybody wants to unmute themselves, maybe, I don't know if you guys attended yesterday's or the day before's lectures. If you did, maybe you can tell us what you liked and what you didn't like. So if we decide to do this again in the future, it would be helpful to see what we could improve on, and just anything that you guys, any comments that you have would be nice. Or if you're afraid of unmuting, you can put it in the chat. If not, then I think we can finish this recording, and we can send out all the lectures, recorded sessions, and along with their answered questions. And if you have any questions, please feel free to email us back, and we'll get back to you as soon as possible.